In the last video, I showed you what it looks like when a function has a limit as you approach a particular x value. In this video, I'm going to show you what it looks like when the limit does not exist. But first, let's look at an example that does have a limit so I can just remind you what that would look like. So we have this piecewise function, and this says that f of x will equal a value of 1 whenever x does not equal 2. So everywhere except for 2, the function is just going to simply have a value of 1. And then the function will equal 0 when x equals 2. All right, so when x is not equal to 2, the function has a value of 1. So let's start with that. All right, so if the function has a value of 1, then that means it's just going to be a straight line. All right, but I'm going to stop short of 2 and sort of skip over it in a way. Because the function's going to have a value of 1 everywhere except for 2. So it's important that we leave this hole right here to show that the value of the function is not going to continue to be 1 right at an x value of 2. At the x value of 2, the value of the function is 0. So right here at 2, the value of the function is going to be down here. All right, so here's what this piecewise function looks like. Now let's talk about limits. What happens as the x values approach 2 from the left? This is easy because this is just a flat line. So everywhere to the left of 2, the value of the function is exactly 1. So we can easily just say that f of x approaches 1 because it's actually 1 the entire time on the left side. So it certainly approaches 1. It's always 1. What about as x approaches 2 from the right-hand side? It's going to be the exact same situation. This is just a flat line at 1. So again, we can say that f of x approaches 1 because the value of the function is 1 the entire time on the right-hand side. Because f of x approaches the same value from the left and from the right of x equals 2, we can say that the limit of f of x as x approaches 2 is 1. And here's the notation that we use for that. We say the limit of f of x as x approaches 2 is equal to 1. All right, now notice it doesn't really matter what's happening at 2. We talked about what the value of the function is as we approach 2 from the left, and what's the value of the function as we approach 2 from the right. In both cases, it happened to be 1 for this particular problem. But we did not talk about what's happening at 2 because it doesn't matter. In this case, at 2, the value of the function happens to be 0. It jumps down here. But what if we changed that? What effect would that have on the limit? So let's say instead of the value of the function being 0, what if the value of the function was 2 at x equals 2? So that means instead of being down here, the value of the function would be up here. So the function would look like this instead. Would that change the limit? No, because the limit has nothing to do with what's happening exactly at the x value. Still, the value of the function is 1 as we approach from the left, and the value of the function is 1 as we approach from the right. So that means the limit is still 1. So just nail down in your mind that it doesn't matter what's happening at the x value of 2 for the limit to exist. This could even be undefined. So now that we've reviewed what it looks like for a limit to exist, let's look at an example when the limit does not exist. So let's show that the limit of absolute value of x divided by x as x approaches 0 does not exist. So let's break this down. Let's look at the numerator first to get a feel for what this function is. So in the numerator, we got simply the absolute value of x, and we should be fairly familiar with this particular function. We should know what the graph of this looks like, right? Let's just do a quick sketch and refresh our memory. Hopefully you know that the absolute value of x winds up looking like a V, where on the right-hand side, we've got y equals x, to the right of 0, and to the left of 0, we have y equals negative x. For that reason, we can easily write the absolute value of x as a piecewise function, and we can say that to the right of 0, it's just going to be x. So the value of the function will be x whenever x is greater than or equal to 0. On the left-hand side, it's negative x. So we can say the value of the function will be negative x whenever x is less than 0. It doesn't really matter which one of these I picked to be the or equal to. Don't focus too much on that. It doesn't really matter right now. Okay, so that's just the numerator. So here comes this modification. So we have to take this, and now we're dividing by x. So what will that look like? So if I take my absolute value of x, and now I'm going to divide everything by x, can I rewrite and modify my absolute value? Can I modify my piecewise function to reflect this dividing by x? Well, let's just take each portion and divide by x and think about what will happen. So if I divide that first piece by x, and what will happen if I divide the last piece by x? Now, for the most part, we can say that if we have x divided by x, that's just going to be the number 1. All right, anything divided by itself is 1, except for one thing. There's one value of x that you're not allowed to divide by, and you're probably thinking it right now. You can't divide by 0. So a minute ago when I said it's going to be x whenever x is greater than or equal to 0, well, as soon as that becomes x divided by x, we can no longer say that it's going to be 1 when x is equal to 0, because that's going to be undefined. So I'm just going to take away the little equal to sign and just say when x is greater than 0, the value of the function will be 1. At 0, it's just plain undefined. So we don't need to write anything about that in the piecewise function. Anyway, if we have negative x divided by x, that's going to be negative 1. Again, as long as x is less than 0, can't be equal to 0 still. So here is the piecewise function for our original function. So let's do a graph of this so we can analyze and see what the limit, well, so we can see why the limit doesn't exist. All right, so here comes a quick sketch. All right, so to the right of 0, we have a value of 1, so let's set that up. And to the left of 0, the value of the function is negative 1. Right at 0, it is undefined. Okay, so I'm going to put open circles at both of these points. The function is undefined at 0. So again, when x is greater than 0, the value of the function is 1. So up here, the value of the function is 1. When x is less than 0, or to the left of 0, the value of this function will be negative 1. So that's going to be down here. So here is a sketch of what this function actually looks like. Now, when we talk about limits, we want to talk about what is the value of the function as we approach a particular x value from the left and from the right. In this case, we want to know about the limit as x approaches 0. So we have to look from the left and from the right. So what happens as x approaches 0 from the left? Well, as x approaches 0 from the left, the value of the function is negative 1 the entire time. So we can definitely say f of x approaches negative 1. Now, as x approaches 0 from the right, the value of the function is 1 the entire time. So if it's 1 the entire time, then we can definitely say that f of x approaches positive 1. Notice that these values are different. For a limit to exist, the value of the function has to be the same as we approach a particular x value from the left and from the right. These have to be the same. Because the behavior is different on the left and the right, that's why the limit does not exist. So again, different left and right behavior near 0 means that the limit does not exist. Let's take a look at another example. Does the limit of 1 over x squared as x approaches 0 exist? I think we should take a look at the graph for this one. All right, so here's what the graph of the function looks like. And the question that we have to ask ourselves whenever we're talking about limits is, what is happening to the value of the function to the left, and what's happening to the value of the function to the right of a particular x value? In this case, we want to know the limit as x approaches 0. So what's happening as we approach 0 from the left, and what's happening as we approach 0 from the right? Whenever I write down a statement like this, it reminds me of end behavior, so don't get confused. Remember when we do end behavior and we always say, as x approaches negative infinity, what's the function doing? This is very similar to that, but it's sort of inside out. We're not asking what happens as x approaches negative infinity. We're asking what happens as x approaches 0. So, as we approach 0 from the left, notice that the function is going up, 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 up. We have an asymptote here. It's never going to reach 0. The value of the function will just go up to infinity. So f of x approaches infinity, positive infinity, as we approach 0 from the left. How about as x approaches 0 from the right? Well, as we approach 0 from the right, the value of the function again goes up, 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 up into the sky. Again, it's approaching positive infinity. Now, even though these are the same, infinity and infinity again, still the limit does not exist because this is unbounded. For the limit to truly exist, the value of the function has to approach a number, not infinity. Again, because the value of the function is unbounded near 0, the limit as x approaches 0 does not exist. All right, let's look at one last example. Does the limit of sine of 1 over x as x approaches 0 exist? Things get a little strange when we start dealing with the limits of trig functions. Of course, trig functions are periodic functions, and if we were talking about the basic graph of, let's say, f of x was simply equal to the sine of x, remember that it would work like this. Here's 1 and here's -1. The sine function simply would start at 0, and then it goes up and down and up and down, and it does that forever in both directions. So periodic function. So how will a limit work for a trig function? So let's use a table of values to help guide us. But first, let's remember that 1 over x just means the reciprocal of x. Right? This makes sense because, for example, if let's say we had 1 over 3/5, you would have to multiply by the reciprocal, and this would be the same thing as 5 over 3. So 1 over something is just the reciprocal. So keep that in mind as we do this, because we have the sine of 1 over x. So x is 2 over pi, so that means the sine of this is going to be the sine of pi over 2. All right, because 1 over x is just the reciprocal of x. So the sine of 1 over x is just the sine of the reciprocal, the sine of pi over 2. Now, remember your unit circle. I will try to put a little pop-up video up here in the upper right-hand corner if you need a review on the unit circle. But you won't need that review if you understand that at the top of the unit circle here would be pi over 2. And we know that the sine is always the y value on the unit circle. So at pi over 2, this is the unit circle, so that means the radius is always 1. So that means the y value at pi over 2 would be 1. So the sine of 1 over x, in this case, is the sine of pi over 2, which is 1. Now, what about the sine of 3 pi over 2? Well, this is 1 pi over 2, 2 pi over 2, 3 pi over 2 would be right here. The y value at this position is -1. So this would be -1. And again, I'm just doing the reciprocal. I'm not going to write this down every time, but just understand that because we're doing 1 over x, and that's the reciprocal of 2 over 3 pi is the same thing as 3 pi over 2. And the sine of 3 pi over 2 is -1. Okay, the reciprocal of this is 5 pi over 2. So that means the sine of 5 pi over 2. Well, this is 1, 2, 3, 4. 5 pi over 2 is going to be back here at the top again. And that's going to be +1. Okay, similarly, if I do the reciprocal of 2 over 7 pi, that's going to be the sine of 7 pi over 2. And guess what? You're probably seeing the pattern by now. 7 pi over 2 is going to be back down here at the bottom, which is -1. All right, and by now you've guessed where we're going with this. As I keep going, it's just going to keep oscillating between +1 and -1. All right, the reciprocal of 2 over 9 pi is going to be 9 pi over 2. And the sine of 9 pi over 2 is back at the top at +1. And this is going to go on forever. So just one more time, the reciprocal of 2 over 11 pi is going to be 11 pi over 2. And 11 pi over 2 is back down here at the bottom, back down here at -1. Now let's talk about the fact that we're supposed to be finding the limit as x approaches 0. With these values that I've chosen for the x values, can you see that we are in fact approaching 0? The numerator is always 2. But look what's happening. I have 2 divided by pi, 2 divided by 3 pi, 5 pi, 7 pi, 9 pi, 11 pi. I'm always dividing by a bigger number. So if I keep taking 2 and dividing by a bigger and bigger number, can you see that the overall value of that expression is approaching 0? If I keep making the denominator bigger and bigger, the value of the fraction gets smaller and smaller. So in fact, these x values are approaching 0. But as you can see from what we've done so far, as the x values are approaching 0, we keep going back and forth between +1 and -1, +1, -1, +1 and -1. And guess what? This would keep happening forever. As you get closer and closer to 0, the value of the function is not going to approach a single number. It's going to keep oscillating between +1 and -1. So for that reason, the limit does not exist. So in other words, this is a third way for a limit to not exist when you have oscillating values as you approach the particular x value. So let's summarize what we just discussed. So here are 3 situations when the limit does not exist. One is when the function approaches 2 different values from the left and the right. That's the situation we saw in example 2. From the left, the function was at -1. From the right, the function was at +1. That's 2 different values, so the limit did not exist. A second situation is when f of x is unbounded near a given value of x. That's what we saw in example 3. As x values approached 0, the value of the function approached infinity from the left and from the right. That is unbounded. It's approaching infinity. That's not allowed when you're talking about a limit. So that a limit like that does not exist. And of course, the third situation is when the function oscillates as you approach a given x value. And that's the situation that we just saw, where as we approach an x value of 0, the value of the function kept oscillating between +1 and -1, +1, -1, +1 and -1. So the limit does not exist when the value of the function oscillates or jumps back and forth between values.